Hi everyone. We are still looking into introductory topics for the Calculus 1 course. In this second section, we will examine laws of exponents. Recall that exponents are used to avoid repeating the multiplication of the same number over and over again. We'll assume for now that the exponent is some natural number. Writing x times x times x times x over and over again, perhaps n times, can be synthesized by writing x to the power n. In this case, the superscript, or the exponent n, is there to represent the number of repetitions with which x multiplies itself. For example, here we have 5 multiplying itself 6 different times. 5 to the power 6 is a more succinct way of writing 5 times 5 times 5 times 5 times 5 times 5. The number may change as we do a progression of multiplication. In this case, 2 multiplies with itself 3 different times, and 3 is multiplied 4 different times. And therefore, 2 to the power 3 takes care of representing the multiples of 2 that appear in 3 different cases, and 3 to the power 4 takes care of representing the fact that 3 is multiplied 4 different times. In this last example, we have only one appearance of the number x. We have 4 repetitions of the number a, and we have 3 repetitions of the number y. The order in which these multiplications appear is irrelevant, and therefore we can write x to the 1, y to the power 3, multiplied with a to the power 4, to present a more synthesized way that is of representing the product that appeared originally. Of course, x to the power 1 can simply be written as x. Laws of exponents are a series of properties that can be used to combine numbers together where exponents are involved. A to the m times a to the n, when the base is common and a multiplication takes place, the exponents can be added. If a division takes place with a common base a, then the exponents can be subtracted. Having an exponent of 0 makes a to the 0 equal to 1. We're assuming here that a is a non-zero number. Negative exponents simply mean that we can displace where the a is located. A to the minus n can be replaced by the fraction 1 over a to the n. And likewise, 1 over a to the minus m means we could in fact rewrite as a to the power m at the numerator. If numbers are multiplied with a common exponent, the exponent can be distributed to each term. So ab globally to the power m becomes a to the power m, b to the power m individually. The same is true about the division of two numbers with a common power m. Consecutive exponents can be multiplied. A to the power m, all to the power n, can be combined as a to the power mn. In the following examples, we'll work on simplifying expressions by using the laws of exponents. In this first example, we have x to the power 2, all to the power 3, divided by x to the 4. The first operation we'll take care of is handling the consecutive exponents appearing at the numerator. X to the 2 to the 3 can be combined as x to the 2 times 3, so x to the 6. Then occurs a division with a common base x, in which case the exponents can be subtracted, leaving x squared. Here's another example involving multiplications and divisions, all with terms whose base is x. Let's work on the numerator first of all. Common base x in a multiplication means the exponents can be added. The fact that minus 2 is a negative number doesn't prevent you from adding the exponents. Minus 2 plus 5 will become 3. Now appears a division, in which case exponents can be subtracted because the base is common. X to the power 3 minus minus 3 then simplifies to x to the power 6. Again, now we have more and more complex expressions taking place. The first property we'll use is the fact that we have a product of two expressions, x squared and y to the minus 1, with 3 acting as a common exponent to both of these. The property that we saw earlier about ab to the m, allowing you to replace by a to the m, b to the m, is what will apply. So the exponent, or the power 3, has been applied to both the x squared and to the y to the minus 1. We've now created consecutive exponents, and recall that those can be multiplied. X to the power 2 to the power 3 is x to the 6, because 2 times 3 is 6. Minus 1 times 3 is minus 3, and therefore y to the minus 3 is a simplified version of y to the minus 1 to the power 3. At the bottom there is a lonesome y still taking place, and we will choose here to rewrite y to the minus 3 as y to the power plus 3 by using the property for negative exponents. At the denominator, we now have a product of two terms with the same base, and therefore the exponents can be added. Although we don't see it, the term y has a power 1, which added to 3 becomes 4. Again, complexity level is increasing here, where we have multiple operations taking place. In particular, we also have a division, which, if you recall from our previous videos, can be replaced by the product of the reciprocal. That explains how dividing k to the 3 over p squared has been converted into a multiplication by p squared over k to the power 3. First and foremost, we will apply the exponent minus 1 on the individual terms of the fraction, k to the minus 2 over p to the power 3. Notice how we've also joined the product of the fractions into one single fraction. That's a property that we've seen again in the fractions section. Now consecutive exponents, minus 2 and minus 1, have been multiplied together as to produce the k to the power 2 term. At the denominator, consecutive exponents 3 and minus 1 have been multiplied to create p to the minus 3. Now looking at the exponents for k and p individually, we have k to the power 2 at the top and k to the power 3 at the denominator. This division allows you to subtract the exponents, k to the 2 minus 3. At the numerator, we have p to the power 2 dividing p to the minus 3 at the denominator. Again, division allows you to subtract the exponents. 2 minus minus 3 will become p to the 5. As a last step, we try to avoid leaving negative exponents, and therefore we will rewrite k to the minus 1 as 1 over k, and as it is multiplied with p to the 5, that creates the fraction that you see before you.